Okay, so this is question 11 of the magnetic fields homework booklet. So in question number 11, what we have is we've got a figure down here that shows a negative ion, and it has a charge of -3 times the charge of an electron. This particular ion is free to move, and it's moving in a uniform electric field. When the ion is accelerated by the field through a distance of 63 millimeters and it's moving parallel to the field lines, its kinetic increases by 4 times 10 to the minus 16 joules. The electric field is in this direction. We're asked, first of all, to state and explain the direction of the electrostatic force on the ion. Well, this is a negative charge, and if you remember, you should know that the electric field lines show the direction that a positive test charge would move in. So because this is negative, it'll go in the opposite way. So the way we would say this is we would say that the force is going to the left. So we've stated it. We then need to explain why that happens. And that happens because the ion has got a negative charge. And so then if we want to add some more detail, we'd then say so therefore it moves in the opposite direction to the direction of the field lines. So for 2 marks, the first point is 1 mark, and you simply then have to say that the ion has a negative charge for the second mark. For part 2, we're then asked to calculate the magnitude or the size of the electrostatic force acting on the ion. Now this is a slightly tricky question because we're dealing with energy, not with, for example, things like the distance between plates or something like that. Now because we're dealing with the energy, we can use this equation. So this is the work done in joules, and this is equal to the force multiplied by the distance. So this is often an equation that's associated with mechanics, but we can use this equation in this situation as well. So if we rearrange that, then the force is equal to the work done divided by the distance. Now the work done, we're told in the question, is 4 times 10 to the minus 16 joules, and that happens over a distance of 63 millimeters. So that's 63 times 10 to the minus 3 meters. And if we do that on our calculator, we find that the magnitude of the electromagnetic force is 6.3 times 10 to the minus 15 newtons. Now that we know the force, we can answer part 3, which is to calculate the electric field strength. Well, electric field strength is defined as the force per unit charge. So to work out electric field strength, we simply do the force we've worked out up here, the 6.3 times 10 to the minus 15 newtons, and we divide it by the charge of our particle. So this is our force. The charge of the particle is 3 lots of the charge of an electron, so 3 times 1.6 times 10 to the minus 19, and so therefore the electric field is 1.3 times 10 to the minus 4. So in part B, we've got another figure to look at. So figure 2 shows a section of a horizontal copper wire, so this wire here, and it carries a current of 0.38 amps. We've then got a horizontal uniform magnetic field. It has flux density B, and that's applied at right angles to the wire in this particular direction here. So the first part of this part of the question, we're asked to state the direction of the magnetic field, and then we're asked to explain how we arrive at this answer. So basically we've got a current going this way, field going this way, so this is again Fleming's left-hand rule. So if we take our left hand, we point our second finger from left to right, and then we rotate our first finger so that it's basically pointing towards us, so it's pointing out of the paper while keeping the current going from left to right. If we do that, then our thumb points downwards. So we need to state the direction, so that's downwards. We then need to explain how we arrived at it. Well, we basically just say Fleming's left-hand rule with current going to the right and the field going out of the paper. So therefore the force is downwards. 1 mark for downwards, 1 mark for this explanation. In part 2 of this particular question, we're then told that this copper wire contains this many free electrons per cubic meter. So every cubic meter's got this many free electrons in it. The section of the wire is 95 millimeters long, and it has a cross-sectional area of this amount of meters squared here. We're asked to show that there are approximately 4 times 10 to the 22 free electrons in this section of wire. So the way we're going to do this is we basically need to work out the volume first. So obviously volume is the area of the cross-section multiplied by the length. So therefore the volume is 5.1 times 10 to the minus 6 square meters multiplied by 95 times 10 to the minus 3 meters. So we've converted our millimeters into meters. And if we do that, we get 4.845 times 10 to the minus 7 cubic meters. Now in 1 cubic metre, there's 8.4 times 10 to the 28 free electrons. We have this many cubic metres, so if we just multiply this number by the number in 1 cubic metre, that'll tell us how many electrons we've got. And if we do that, we end up with 4.0698 times 10 to the 22, which is about 4 times 10 to the 22, which is what we were asked to show. Because we have to show it, that's why I've written this answer down to quite a lot of significant figures. The final part of this question is we're now asked to calculate the flux density of the magnetic field. We're told that the current of 0.38 amps means that there is an average velocity of an electron of 5.5 times 10 to the minus 6 meters per second. And the average magnetic force on one electron is 1.4 times 10 to the minus 25 newtons. Now there are two ways to do this. There's kind of an easy way and there's a more difficult way, but they both end up with the same answer. The easy way is simply to use this equation here. So the force is the magnetic flux density multiplied by the charge and the velocity. So if we rearrange that, the magnetic flux density is the force over the charge and the velocity. Now the force is this number here that we're told, so that's the force on one electron. This is the charge of one electron, and this is how fast the electron's moving, and if we do that, we end up with 0.16. So our flux density is 0.16 Tesla. Another way to look at it is to calculate the magnetic flux density using this formula. So F is the force on all of the electrons in the wire. I is the current, because that's all of the electrons that are in the wire, and L is the length of the wire. So if we rearrange this for B, we end up with this. So the force is simply equal to the total force altogether. Well, this is the force on one electron, and this was the number of electrons that we found in the previous question. So if we multiply that together, that gives us the total force acting on the wire. This is simply the current, and then this is the length of the wire, and if we put these numbers into our calculator, again we end up with 0.16 Tesla. To be honest, I think I'd go with this method. However, if you use this method, it's equally valid. Okay, so that was question number 11 of the Magnetic Fields homework booklet.